All right, so you guys have had a couple of minutes to work on this. A lot of you are getting there or close to the end here. So let's just kind of make sure everyone's on the same page here. You were to graph two things in the same window. One was the graph of 1 plus sine of x, and they set the window there of negative pi to pi on your x and negative 1 to 2.5 on your y. And then it said in the same viewing window, graph the tangent line. So real quickly here, the tangent line, we've done this in the past, the equation of the tangent line. You have to take the derivative, so f prime of 0 is what we're looking for, okay? Because we want it to hit the point 0, 1, okay? So, now that I have the screen unfrozen, you can actually see what I'm writing. Okay, so f prime of 0. So f prime is just cosine x. You guys got that. So we're doing cosine of 0, which you guys know is 1. All right. Now that is the slope of the tangent line. And then, however you find equations of lines, you might have just recognized, hey, 0, 1 is on the y-axis, so that's my y-intercept. So the equation is y equals x plus 1. Or you may have looked ahead and noticed that the table down here has y equals 1 plus x, and gotten your equation of the tangent line from there too. But anyways, it's a good exercise for you to get that equation. So we graph them both, and I want you to be able to see this, so I'm going to do this. I'll have it up here where you can see, and I'm going to hit record on that too so it records on the movie. All right, so there's what it looks like on that window that we were given. Okay, and you can see the point of tangency there at the point 0, 1. All right, so now it says zoom in twice on the point of tangency. All right, so we hit zoom, and we're going to zoom in. Okay, and we zoom in there. And wait for it to graph. It's really slow for some reason. Okay, so there you can see this is where having the color is really nice. Those of you who have the 84 color, it is nice to have that. You can see the distinction still. But then we're going to zoom in again. So zoom 2, put it right there on the point of tangency, 0, 1. And notice here now, the next question was, does your graphing utility distinguish between the two graphs? Well, especially if you have a black and white one, you're not going to see any difference. It's just going to look like one line. Here you can kind of see both the blue and the red showing up. But you'll notice here, even though we know 1 plus sine of x is not a straight line, because we've zoomed in so close, it looks straight. Okay? We've zoomed in so close here that it looks straight. So our graphing calculator does not distinguish between the two graphs on this interval. Okay? At least from what we can see. So the next thing we are asked to do is use a table to compare the two graphs. So there's a cool thing that you can do with the table. We haven't used tables a whole lot, but if you go to second table set, okay, you'll notice table set and delta table. We've worked with that before. Something different though here is you can actually tell it to ask you what the independent variables you want are. Okay, we could have used this back when we were finding limits with the table as well. But I'm going to hit, make sure that that is ask on the independent variable. And then I'm going to hit second table to view my table. And you'll notice, since I already did this once, the values here I typed in. Okay, if I wanted another value of x, you know, if I wanted it when, you know, x is 0.7 or something, I could just type in a 0.7 and it'll actually calculate both functions at 0.7. Okay? But now we can look at the table. At negative 0.5, the 1 plus sign is 0.52057, whereas the line is 0.5. At negative 0.1, we have 0.90017 as opposed to a 0.9. Then at negative 0.01, we have a 0.99 here and a 0.99 here. At 0, they both equal 1. We knew that because we made the line hit the graph at that point. But then after we get past it, at 0.1, we have 1.01 and 1.01. At 0.5, or I'm sorry, at 0.1, we have 1.0998 and 1.1, and here we have a 1.4794 and a 1.5. Okay? So I'm going to get out of this video. If it'll let me. And now we can see in our table, as the values get closer to 1, what can we say about the y values of these two functions, the function 1 plus sine x and the tangent line?
Close.
Huh?
Very close.
They're very close. In fact, as we're really, really close to 0, you know, they're virtually identical. Now, if we went out enough decimal places, we would eventually see a difference, okay? But what we have here is, because we have zoomed in so close to this point of tangency, where they are equal, if we're close enough to that point, the line will be approximately the same value as the function, okay? Now, what this tells us then is what we see down here. And that is the tangent line gives us an approximation. We call this the tangent line approximation of the value of the function at some number c. We could also call this the linear approximation. Okay? Now, the idea here is, as long as we are really, really close to the point of tangency, we could just use the line to approximate the value of the function. Okay? And we're using the same principle that we do as we look outside and we say, oh, that field out there is flat. When the reality is, we know that we're standing on top of a sphere, right? So is anything actually flat? No. Everything is curved. It's just so little curved. We're zoomed in on such a small part of that enormous sphere that we call the Earth that it looks flat. Same thing with that 1 plus sine of x. We know it's curved, but when we zoom in close enough, it looks like a straight line. Okay? Now, one application of this that people have used in the past was in finding values of trig functions. Before the advent of the scientific calculator, when you could just type in sine of whatever, we used tables. Okay? Now, these tables, we used something that was called linear interpolation, okay? And I'll just give you a quick example of what I'm talking about here. Let's say that I wanted to find the sine of, say, 46.8 degrees. Well, now we just punch that into our calculator. It's really nice, so we can just figure out what it is, okay? However, before we had the scientific calculator, we had to rely on a table. And obviously a table can only be so precise. So what you would have is in your table, you would have, let me actually move this down a little bit. Oh. You would actually have the sine of 46 and the sine of 47 degrees. Okay? Well, sine of 46 is 0.7193. We'll round to 4 decimals. 0.7193. And the sine of 47 is 0.7314. Okay? Now, because those are only 1 degree apart, it's very, very close, we could assume that sine was linear between them. Now, is sine linear? Obviously not. But because it's such a small range, we could assume that briefly in order to approximate what the sine of 46.8 degrees is. Okay? So, what we have here is we could then say, okay, well, I see that sine is increasing from 46 to 47. So it's going to be that 0.7193 plus something, right? Well, then what we would do is we'd say, okay, well, I want 46.8. So I want 8/10 of the difference between those two values. 8/10 of the distance between those. All right, so if I subtracted those two, I'd get a 0.0121. Okay? And if I work that out, I have 0.0121 times 0.8, which is a 0.00968. Okay? So this is going to be 0.7193 plus a 0.00968. So I add that together, 0.7193, and I get 0.72898. Okay? Now, if I just punch into my calculator sine of 46.8, I actually get 0.7289686. So this is actually accurate to 4 decimal places. Okay? And it is that because we have it only 1 degree apart. Okay? But this is an application where even though we didn't have the full equation of the line, we were using this same concept where we looked at a very narrow range, assumed it was linear, and then we're able to use the line to help us approximate the value of the function. Okay? So, again, that's just one application, and until, like I said, until we had scientific calculators, that's how we had to do this. Okay? That's how we had to, we'd have a table in the back of our math book, and we'd have to figure it out this way. Now, I'm not that old to where we had to. We did this as like an exercise, but I remember the math books we used were from, I think they were from like 1991 or 92, and they still had the tables in the back. So it wasn't too terribly long ago, 25 to 30 years ago, people were still using tables like this to figure stuff out, and you still were able to get very, very accurate results, as you can see. Okay, so the whole idea here, though, just to sum this up, is that if you can get the equation of the line, notice here I'm using the derivative at a specific point as my slope, and then x minus the x coordinate and we have y minus the y coordinate. That's our equation, and we have here the whole equation of the line. But we can use that to approximate the value of the function anywhere. Or I should say close to that point of tangency. Okay? And that's it, okay? Just to illustrate this last statement here. In other words, as x approaches c, the limit of the y, which is the line, is going to equal the function evaluated at c. Okay, that's what this whole thing is saying. All right? So that's it.